Hi, my name is Walid. I am a PhD student in UMass. I'm working with Prashant. I'm a final year PhD student. And I'm going to talk to you today about sustainable computing. So I will give you an overview of what is meant by sustainable computing and some of the work that we and other groups have been doing in this domain. So before I start my lecture, I would like to give you a quick brief about myself. So I've been here almost 5 years. I've been working on machine learning systems. I've been working on sustainable systems as well, and I've been working on machine learning for sustainable systems and sustainable machine learning systems. So anything that contains machine learning and sustainability, I kind of like it. So I've been lucky to work here in UMass. I've been published many papers across many conferences. And I want to ask a question before I start the lecture. What is sustainable systems? So when people mention sustainable systems, there is many aspects that you should be considering. You should be considering the supply chain, that you have to get the products that you are using, what is the energy efficiency of the products that you are currently using, and what is the source of energy that you are currently using. So are you using brown energy or are you using green energy? And how you are disposing the products are using. This not only applies to computers. This applies to the grid, how the power generators are built, what is the and how is the end of life of these generators, buildings, what is the products that you are getting in your buildings in terms of appliances, what is the energy efficiency of these appliances that you are using in your home, what is the energy sources that you are using in your homes. And this also applies to transport. So if I have an EV, yes, people say that an EV is better, even based on the efficiency argument, that the energy efficiencies from electric vehicles are better than the energy efficiency of regular vehicles. But still, I want to make sure that my EV is being charged on clean energy, or at least decrease the amount of brown energy that I'm used to run my EV. And of course, this applies to compute. So thinking about compute, how do I build the hardware that I'm going to use? What is the energy efficiency of the hardware that I'm using? What is the sources of energy that I'm going to use? And how I dispose and recycle the electronic waste. Today, I will mostly focus on compute, but many of the things that I will talk about today applies to many other domains. So when I'm considering carbon emissions of a service, and specifically computing, I'm considering the extraction of the material, I'm considering the design, the manufacturing, the transport, and the usage of this device. So in computing, usually people refer to the entire from the extraction till the end of life, except for usage, as embodied emissions, and they consider the usage emissions as operational emissions. Okay, and when we discuss data centers, we should understand that computing demand is growing. So computing now is everywhere. So we have been using computing in all domains that you can think of. You have been using domains in social media. We have been using domains in chemistry. Everything now is about computing. AI, of course, is one key attribute, is one key type of computing. And as an industry, we should understand what is the carbon emissions of computing and our industry in general. So ICT is responsible for 1.5 to 4% of the global emissions. This is higher than the aviation industry. Aviation industries that have no electrification, we are all the electrifications and all the optimizations we have did, we are now more than the aviation industry. And there is estimation that we will reach 6 to 14% of the global emissions by 2040. And data centers is a huge part of these emissions. So there is different estimates and it changes per country. So data centers estimates states that it's from 20% to 40% of the global emissions goes to data centers. And AI is not doing us any help. So AI is increasing, the demand for data centers and for compute is increasing. So a recent analysis states that the increase in AI have increased the data center power by 160% compared to analysis that was in 2020. So 3 years apart, the reality and the estimates are differed by 160%. So this is huge. So again, carbon emissions of computing are classified into embodied emissions and operational emissions. If we look at a specific device like a TPU, we will find that most of its emissions are operational emissions. So in this case, what we need to optimize is its operational emissions. We need to run it in more green energy sources as much as possible. And this also applies to data centers. So data centers are not only TPUs and GPUs, they have other things. But in general, people say that 80% of the emissions of data centers are operational and 20% are embodied. If you consider it something like a phone, this is based on the LCA analysis that Apple have produced. 80% of the emissions from an iPhone is embodied emissions because it has very complex hardware that consumes a lot of energy to produce, and only 20% is operational. And this happens for two reasons. First, the lifetime of a phone is very little compared to a data center and servers. So servers usually have a 3 to 5 years cycle. And however, a phone is typically much shorter. And a phone usually consumes much less energy than a data center. So the embodied emissions is considered the major part. So to optimize carbon emissions in general, I should be able to think of how do I optimize the operational emissions and how do I optimize the operational emissions. So I optimize the embodied and optimize the operationals. To optimize the embodied emissions, I should be able to understand the relation between the design that I'm using and the embodied emissions. Usually, more complex designs means more higher embodied emission because it's more complex to manufacture. So there is papers that have been analyzing the embodied emissions. How does different design decisions affect the overall embodied emissions of a hardware? There is papers that appears. Usually, this work is done by hardware architects, where they analyze the different decisions, and there is also work by different groups that another way to optimize the embodied emissions is to extend its lifetime. So researchers have analyzed that the e-waste from phones in particular is very high. People keep the phone for 1 or 2 years and then throw it. So researchers have proposed ways to extend the lifetime by building clusters out of phones and showed that in many cases they achieve very high and good performance comparable to a server. And there are other ways to extend the lifetime of hardware. So there is this paper from Microsoft Research have shown that by extending the lifetime of specific components, you can basically reduce the embodied emissions highly. And in particular, they showed that memory, SSDs and RAMs have very high embodied emissions. And by extending its lifetime, you amortize this embodied emission over longer periods, hence using less new hardware and still achieving good performance. So in this, again, people care about performance, people care about the cost of but also people should care about the embodied emissions and the cost of hardware that they have. So to optimize operational emissions, it's a little bit of a different story. So I need to optimize. So the carbon footprint of a server is based on two components. I need to understand the amount of energy that I'm using and the source of energy. And by multiplying the energies that I'm using times the carbon intensity, I get what's called carbon footprint. So if I want to optimize the energy or decrease the amount of energy that I'm using, I have two ways. I can use better algorithms. I can develop better algorithms, better ways, optimize my code. So basically using less cycle to do the same task. And I can also enhance my power efficiency. I need to be able to do more with less power. The second approach is to optimize the carbon intensity. I need to be able to integrate more and more clean energy into my system and into my grid, and also implement carbon aware scheduling. So basically following where where clean energy is, and try to use more of it. So in the rest of the talk, I will focus more on operational emissions, and I will show you a couple of research that we have did to optimize the carbon efficiency of computing. So if we consider energy efficiency in general, there is data centers usually host hundreds and thousands of CPUs and GPUs. So researchers have analyzed, or basically there is a law called Kumi's law, similar to Moore's law, that this law basically says that energy efficiency of hardware doubles every 18 months. So basically, if I'm a data center and I need to optimize my energy efficiency, I basically should upgrade my hardware whenever a new hardware or whenever a new or a more energy efficient hardware is there, so that I can benefit from these efficiencies that comes by the newer hardware that is appearing. So this is what basically data centers have been doing. They usually have an upgrade cycle every 3 to 5 years and change the hardware that using, so that they can be as more energy efficient as possible. Energy efficiency in this case is tied directly with cost efficiency, because if you are using less power, you are basically paying less to use power, and then you can have more profit from the hardware that you currently own. There is also 20 plus years of research on optimizing the energy efficiency and designing resource management techniques, but I will not go through it. However, I want to highlight something, that this approach was very successful. So compared to, in this analysis, they show that between 2010 and 2018, the total energy demand have only increased by 5%. This is the global energy demand this is the US energy demand of data centers, or the global. It's either the US or the global, but it only increased by 5%. However, the compute demand measured in millions of compute instances increased by 6 times, or 6.4 times to be exact. This shows a great improvement in the energy efficiency. I'm able to do much more for much less amount of energy. And the estimate was that this is a trend that is going to stay for long. So this paper was published in late 2020, and they said that in 2023 we'll have just 3% more energy, and we will be able to get 14.1x more compute. However, this does not include what happens with AI. AI flipped everything around. AI came with very high demand for energy, and it came with a very high demand and with very high energy. Actually, the estimate says that the amount of energy is now, based on what I saw, it's 160% more than what was predicted at this time. So, which is huge. So the data centers in the last 5 years almost doubled, which is huge. And all the recent studies mention that it will actually increase more. Another aspect of the energy efficiency of data centers which is called PUE, the power usage efficiency, which is basically the total amount of energy that a data center uses over the compute energy. Where an optimal PUE, where all your energy goes towards compute, is 1. So usually data centers, so if I am saying that the PUE of this data center is 1.2, this means that it has a 20% overhead. And this overhead basically comes from the cooling overhead and the power efficiency overhead from the grid and transformers and losses in power efficiency. This usually contributes almost 10% based on Google's data center. And again, for many reasons, including a cost one, data centers are able to optimize their PUE over the last almost 15 years. So at 2018, Google had a PUE of 1.2. Now they have a PUE of 1.8, which changes across season because of different cooling techniques that depends on ambient temperatures that changes across seasons. So the other way to optimize the carbon efficiency or minimize the carbon footprint of computing is to add renewable. So basically, the idea is very simple. Let's replace the fossil fuels that we are using with more green energy sources. So in the recent years, carbon intensity have been increasing because many people have been trying to adopt, or many countries have been trying to adopt this strategy. So all the countries are decreasing their carbon intensity. So for instance, China is going from almost 800 to less than 600 grams for each kilowatt of hour produced in energy. And China is one of the most the countries that have highest like ratio of increase in solar energy. Other countries are also have been investing in this. United Kingdom shows a huge decrease. So it goes from 500 grams in 2000 to almost half of it in 2023. And almost all countries have been trying to optimize their carbon intensity. There are some countries that are outliers. For instance, Sweden highly depends on hydroelectricity with some nuclear as well, so that they have very low carbon intensity profiles. So adding renewables was good for the environment, but it was mostly, but it's now also a cost-efficient approach. So according to the localized cost of energy, which is a measure that, okay, how much I pay for each kilowatt or megawatt of energy that I'm producing, solar is actually right now the most cost efficient, and of course it's very highly carbon efficient source of energy. However, adding more renewables do not solve the problem, because renewables are intermittent. So renewables are, for instance, like a solar is only available during the day. Solar is highly affected by weather. So if there is a cloud, if it became a little bit hot, the amount of solar produced is much less. So the solution that companies and researchers have realized is that, okay, I need to add renewables, but I need to bind, or I need to augment the renewables that I'm adding with load shifting. So based on this article from 2020 by Google, they say that our data centers now work harder when the sun shines and the wind blows. So in translation, this means that where there is more renewable energy, we should be doing compute. And when and where, to be exact. So I didn't say this before, but what is carbon intensity? I keep saying carbon intensity, carbon intensity. So carbon intensity is basically a measure of how clean the energy is. So because the grid depends on many sources of energy, usually the carbon intensity as a signal that represents the weighted average of the carbon of the energy sources that I have right now. So if I'm considering these three sources, if I'm considering like coal that has 760 grams emitted of CO2 equivalent per each kilowatt hour of energy produced, if I'm considering something like solar or wind that basically more or less have 0 grams emitted per each kilowatt of hour produced, I can compute what is called the carbon intensity signal. So the carbon intensity signal in this way, if I have 50% of my energy comes from brown sources and 50% comes from green sources, I will have the weighted average, which is 300 grams per CO2 per kilowatt hour. So because the energy demand changes across time, so as the carbon intensity. So the supply changes across time, the demand changes across time, so as the carbon intensity changes. So if you consider a grid like the California grid, where they have a lot of solar energy, the carbon intensity becomes lower during the day because there is more solar energy, and higher during the night. So the change can be up to 2x difference between the low carbon intensity and the high carbon intensity period. And also the grid and different states have different grids. So each state has its local grid. Actually, each state has many local energy sources. So for instance, there is in Florida, I think they have 8 or 9 different utility companies, each of their own energy mixture, so that they have different carbon intensities. So again, the energy demand supply change across space, so that the carbon intensity. So if you think about it, I should be able to use the spatial, and I should be able to so the temporal and spatial variability underscores the need for carbon-aware resource management. So I should be able to put my compute where the energy is more green. So luckily enough, computing is equipped with many flexibility mechanisms. So I can run in my workload using a suspend and resume manner. I can run my workload or my batch job, for example, a machine learning training job during the day and stop it during the night. I can also do resource scaling. I can use more resources when carbon intensity is low, and slow down and do not use any resources when carbon intensity is high. I can do some sort of approaches that allow me to change the rate of computing. So I will not feed the same amount of data, or I can use something like DVFS that allows me to change the speed of my computations. And I can definitely do spatial shifting. So because computing is well equipped with these resources, unlike other domains, so for instance, I cannot do spatial shifting with home loads because I cannot basically shift my house, but I can do some sort of temporal shifting for EV charging. I should not be charging at this time, but I can charge at another time. So a recent domain have appeared, which is called carbon-aware resource management. And the key idea of this domain is that we should use carbon intensity variation and computation flexibility to optimize the carbon efficiency. And this domain is, and I will continue the rest of this lecture on this domain. So if I want to implement carbon-aware resource management, I need three things. The first one is I need visibility. I need to understand what is the current energy sources that is powering my computation right now. I need to understand how the carbon intensity, for example, changes across time or across locations. Usually, the grids provide a very high reliability abstraction, where when you plug your computer to the socket, you don't know which source of energy is feeding your computing, and it's physically impossible. But by understanding the different energy sources that is currently powers the entire grid right now, you can compute something like a carbon intensity signal that you can use to and make decisions about. And second, I need policies. I need algorithms, and I need techniques that allows me to leverage the computing flexibility with the visibilities I get from the grid, and understanding how does this affect the workloads that I'm currently running, if there is any other constraints I should be considering, and I should be able to provide algorithms that allows me to do this job. And third, I need incentives, because I need to understand the trade-offs that when I do carbon-aware resource management. There is many trade-offs. So I need to understand the trade-offs. I need to understand, and I need to incentivize people to use it. In this lecture, I will talk about the trade-offs, but I will not talk about incentives. So one of the fundamental techniques so before I go to the techniques, so anyone has any questions? Okay. So one of the fundamental techniques of carbon-aware resource management is called temporal shifting. And the key idea of temporal shifting is to match the availability of raw carbon energy with the computing demand. To basically run when the carbon intensity is low. So if I consider a job that instead of running it in a carbon agnostic manner, I can defer its execution to another period of time where carbon intensity is lower. And if the job is very long and deferring it might not give me lots of benefits, I can do it in a suspend and resume manner. So basically, I will start my job, and when carbon intensity gets high over a threshold, for instance, I can stop my job and continue it later. So I will give you an example of a recent work that uses carbon-aware temporal shifting. So the policy is called let's wait a while. So this paper appeared in a couple of years back. So here I will show you 4 different workloads And I assume the power consumption. So this was profiled based on a machine learning training job that uses 0.2 kilowatt hours of energy each hour that it runs. And I'm using here the carbon intensity from California between 2020 and 2022 to demonstrate the benefits of temporal shifting. So here I'm going, the x-axis shows the waiting time. So here I have 4 jobs. The x-axis shows the waiting time, where the waiting time changes from 0 to 60. So the waiting time, or the slack, is the amount of flexibility that I can delay the job for. So for instance, if I have a 1-hour job and I have a 60-hour slack, this means that I need to pick 1 hour out of 61 hours to run my job. So pick the best hours that you can run and just run your job during this hour. Of course, this assumes that I can predict the future carbon intensity, but there is many approaches that allow you to do so in very high accuracy. So here I'm considering 4 jobs. I'm considering a job that will run for 1 hour, and I'm considering a job that runs for 6 hours, 12 hours, and 24 hours. The first thing is that you will realize that with extending the waiting time, I get more carbon savings because you have better options to choose from. So instead of having one option that you need to run the job right now, you have 61 different options if you have a 1-hour job. Another important thing is that there is a diminishing return. So usually, and you will see, and I will mention this word diminishing return multiple times throughout the lecture, there is a point where extending the deadline do not add much benefit. So for instance, if you're considering a 1-hour job, usually you are either in the lowest carbon intensity period and deferring it do not make a difference, or you just missed it and you need almost 18 hours to be again in the same good period. So at 18 hours, it shows that, okay, if I have a 1-hour job, extending it beyond 18 hours usually do not give me much benefits. And this applies to almost all of them. However, there is the way that the knee of the curve is different per the job length. There is a trick in this graph. So this graph shows you that shorter jobs can save more carbon. If I'm computing carbon savings in percentages, this is true, because if I have a 1-hour job, I can move it anywhere and I can get huge amount of benefits. However, if I'm considering the actual saved carbon, it's a totally different story. It's actually the complete opposite, because a longer job means a more compute time, and any amount of saving can actually save much, much more carbon. So in this case, by extending the waiting time, the 24-hour gets huge benefit. And again, this is where the knee of the curve is actually apparent for the 24-hour jobs. So temporal shifting, in summary, temporal shifting depends on the flexibility in completion time, but extending the completion time or extending the slack comes with diminishing returns, where longer jobs have lower relative savings but higher absolute savings. Any question regarding temporal shifting? Okay. So temporal shifting is nice, but there is a fundamental issue with temporal shifting. So if I want to run temporal shifting, I basically need to extend my completion time, as I was explaining earlier. So instead of finishing my job within 24 hours, I needed to finish it over 48 hours or 72 hours. So extending the completion time is one of the fundamental problems of temporal shifting. Another approach or another issue with temporal shifting is that it fails to exploit the differences in carbon intensity. I will run the same rate at this period where carbon intensity is moderate, and at the same rate when carbon intensity is extremely low. So to avoid these issues, we have proposed the usage of resource scaling. So instead of running the job in a suspend and resume manner, I will basically stack the compute across different times. So when carbon intensity is very low, I basically not use one server that like I was using in temporal shifting. I will basically use 3 servers. And this allows me to decrease the completion time And this allows me actually to get more carbon savings because I can run at different rates based on the variations of carbon intensity. So to do so, we propose an algorithm called carbon scaler, which leverages the variability and of carbon intensity as well as the elasticity of workloads. So to do this approach, so in this approach, we have shown that if I have throughput, so if I'm considering that when I scale a job, I should usually understand what is the benefit that I'm getting from using more resources. So usually people try to represent this in terms of the relation between resources and throughput. So more resources means more throughput. However, a key insight that we have when we try to solve this problem is that we will not use the throughput as a measurement unit. We'll use what we call the marginal capacity. So the marginal capacity is the extra throughput that I will get for every added resources. And the benefit of using this will come later in improving the optimality of the algorithm, and I will explain this as I go on. So here the relation between resources and the marginal capacity tells me what is the benefits I'm getting for every resource I am adding. So I was able to use this marginal capacity with carbon intensity to compute what we have been calling the marginal capacity per unit carbon. So this allows me to understand what is the benefit I can get by running at each scale across times. So using this idea of marginal capacity and normalizing by unit carbon allows me to compare decisions across scale and time at the same time. So by being able to compare scale and time at the same by using one unit, I'm able to compare, okay, should I use one resource at this time slot, or should I add another resource at this time slot, or should I use the first resource at this time slot? So by building this on this idea, we have proposed an algorithm. And on a side note, by using the marginal capacity, we were able to map this problem toward other sets of problems called marginal resource allocation, where optimal greedy algorithms exist. So if you took something like 611, you know that in some cases, greedy algorithm can be optimal. And this is one of these instances. So we showed that this algorithm is optimal, and we have which allows to optimize the carbon efficiency as possible as it can be done. So this is one experiment that I want to share with you about the benefits of using carbon scaler or using scaling in general. So here this graph shows me the carbon emissions in gram of CO2 equivalent, where lower is better. So here it shows that our approach compares to a carbon agnostic. We are generally able to save between 51 and 55% without extending the deadline. So if I have a 24-hour job, in this case, I have a 24-hour job, and I need to finish the job within 24 hours. So this will not increase the completion time as per temporal shifting, for instance. One thing also we note is that usually in this case, the GPUs that we are using consume much more power, so that it has much more carbon. And again, this is related to the huge increase in global energy consumption by using more and more GPUs for AI, because GPUs generally have much more energy consumption. So the carbon scaler, so using this approach, scaling or carbon scaler in specific, can reduce the carbon emissions without increasing the completion time. So another approach that people usually try to optimize carbon efficiency with is to use spatial shifting. So I showed you this map earlier, where different states have different carbon intensities. And this also applies to a great extent to every place in the world. That in Europe, there is different carbon intensity across different neighboring countries, even in more differences than here in the US, because at the end of the day, they are different countries with totally different grid systems. But here there is many grids that shares great components of their grids. So if I'm considering spatial shifting, I need to consider one key aspect. So in temporal shifting area, I can delay the job because I'm considering a bad job. However, here in spatial shifting, people usually consider this with interactive workloads. So I need to consider the latency limits that I have. So for instance, if I have a latency limits of 10 milliseconds, then this is where I should be searching. So this is the options that I have. I have 1, 2, 3, or maybe 6 options to choose from. If I have more latency budget, or I can extend my response time by a greater amount, I can have better options. And these go on until I get like to the extent of reaching or running my workload anywhere on Earth. Of course, there are other constraints than latency. For instance, there are laws that do not permit people to put like GDPR in Europe. I cannot host my things in the US, and in the US I cannot host things outside. But this is the general idea. So one key component of the internet is in general is called CDNs. So you will have towards the end of the class a lecture about CDNs. But CDNs are basically, our content delivery networks are basically services that allows you to host media closest to the user in a way that it will and it will have performance because you will host the media that you are watching, a YouTube video or whatever, closer to the user. It has cost and energy benefits because I'm moving the data for shorter distances. So the idea that we were trying to achieve here is that we need to redistribute CDN workloads in a carbon-aware manner. So I need to move, and this paper was published in SOC 2024. So where we use CDN traces from Akamai, we use different traces to build an extensive analysis of what is the possible carbon savings that CDNs can implement. So the results show that by extending the latency limit for a service like CDNs, I can have higher carbon savings. And again, there is a diminishing return. So by extending the latency beyond 60 milliseconds, I should be able to extending the latency limit beyond 60 milliseconds usually do not bring me much benefits. And here the graph shows that by extending the deadline, on average, the latency is not increased by the same rate. So usually by increasing the latency by 30 milliseconds, I can achieve very high carbon savings. So almost 40% reduce the carbon efficiency of a CDN, because CDNs consume a lot of energy because they are global services by 40%. And again, I can do the same in Europe. So we showed that because usually CDNs are not that global. They are global, but they usually, there is no much benefit of moving things across US and Europe. So in Europe, we did the same analysis and showed that CDNs can reduce their carbon efficiency by 80%, considering the same like 70 or 60 milliseconds latency budget. And lastly, I would like to highlight that the savings in Europe is higher because the differences between countries is much higher. So in average, so in Europe, there is many countries like Poland have very brown grid, but there is also many ground like Norway, Sweden have very low carbon, have very green grids because they rely a lot on nuclear energy and renewable and hydroelectricity. So again, higher latency lead to higher saving, but again with diminishing returns. So okay, go. So CDN delivers streaming videos. They deliver all kinds of content. They deliver websites. They deliver, yes, CDN deliver everything. Yes, compared to ML training, yes, it's much less. but at the scale of CDNs, where CDNs are very high scale services, and they consume a lot of energy. So basically, most of the content that is delivered over YouTube or Facebook or any social media are mostly delivered by CDNs runs by this company. There is other companies like Akamai that has provide CDN content delivery services, and we use their data, and it's a well-known fact that they consume, because it's a global service and helps a lot of customers, so that they have high energy footprint and, of course, high carbon footprint. Okay, Nick, more questions? I expected more questions, but we're gonna have questions at the end if I finish early. So one big thing that we have been writing more and more in our recent papers, that in carbon-aware scheduling, there is no free lunch, only trade-offs. So we have discussed, or you may be guessing, one of the trade-offs that we have been seeing is a carbon performance trade-off. But there is also carbon cost trade-offs, and there is carbon energy trade-offs. So again, carbon-aware resource management brings many trade-offs, and it's obvious by now that there is a performance trade-off. So should I run my workload now or run it later? So increase my delay. So usually performance metrics, like response time, it can be in milliseconds, but there is also in batch workloads, there are performance metrics like waiting time that can go for hours. So by deciding whether you run your workload close versus running it far, running it now or running it later, this brings a carbon and performance trade-off. There is also an energy trade-off, which was not really obvious to us or any people who have started working on this domain. So if I want to optimize the carbon efficiency, I basically need to use some sort of a flexibility mechanism. Flexibility mechanism like suspend and resume, flexibility mechanism like using scaling, flexibility mechanism like suspend and migrate my workloads from one place to the other. Every flexibility mechanism of this consumes more energy than just running the workload as is. So if I suspend the workload, if I have a batch job and I suspended it, what will happen is that I will use more energy, because I use energy to store the states that I have. I use the energy to get the states from memory to disk. And if I'm doing migration, I also have to have overhead from migrating my data from one location to the other. All of these are overheads, and all of these bring a carbon energy trade-off. So I will talk about one trade-off. Maybe there is another one I might mention if there is enough time, about scaling. So scaling is good. So I built my entire thesis around scaling. But elastic scaling is not free. So if I'm running at a higher scale, it basically becomes less energy efficient, because when I'm using more resources, I'm getting less out of these resources, I'm being less energy efficient. So basically basically jobs have different scaling profile. There are jobs that have ideal and linear scaling, usually called embarrassingly parallel jobs. By running these jobs at any scale, I usually get almost double the amount. So if I have one resource and I double the amount of resources, I will have double the amount throughput. However, there is many jobs that do not have this behavior. This behavior goes back to Amdahl's law, if you remember what Amdahl's law is, which states something about the ratio between parallelizable and non-parallelizable portions of your code. So all workloads, when you scale them over multiple resources, usually have a communication barrier. For instance, if you consider a machine learning training, at the end of each iteration, or as a mini batch, usually have a synchronization period where you exchange the weights of your model with others. This is a communication barrier, and you will be using, and this will decrease the throughput compared to a linear throughput. So these different scaling profiles is what we have been seeing all along in all our analysis and all the profiles that we have captured. So if you consider here, there is this example where we have 3 workloads. We have 2 machine learning training jobs. One is using ResNet 18, the other is using a smaller model, which is MobileNet V2. And they have an MPI workload that is based on the in-body simulation problem. So this in-body is a problem used to analyze moving objects in space and how the gravitational forces affect each other. It's usually comes as one of the as a type of scientific computing that people use. So if you consider this job, you have 3 different scaling profiles. Actually, we have profile workloads that go across all the scales. We have profile workloads that are almost linear, and we have profile jobs that do not scale beyond a single node at all. So by considering these 3 workloads, I am able to understand what is the benefits and what is the limitation of adding more resources. So we use here speed up, and this is the ratio between number of servers and the speed up. And of course, speed up is normalized to using 1 resource. As you can see, there are jobs that scales almost linearly, and there are jobs that have very, very poor scalability. So if I'm considering these workloads based on the carbon scalar approach, we have seen that by using different workloads are able to achieve different amounts of carbon savings. So here, if you consider this workload that is very scalable, it can go almost to 50% carbon savings. There are some instances that goes to 50% carbon savings. If you consider the MobileNet, there is some instance that goes to 50% carbon saving. If you consider the embody, there is the maximum it gets is amount 30%. What is more important in this graph is that it shows a relation between carbon savings and energy overhead. So the more scalable the job is, the more I can get by with the amount of carbon savings that I get. The energy overhead is included in the carbon saving, so it is not a different metric, and I have to analyze it. But here, I'm just analyzing the carbon saving and the energy overhead within the same workload. So as you see, a workload that is very scalable usually gets very high carbon saving with very little overhead, and if the less scalable the job is, the overhead increases. So if you consider the embody 1K, I was able to get 30% carbon saving. I almost get 30% energy overhead. In some cases, energy is not the limiting factor because there is energy curtailment. There is solar energy that I may be willing as a user to sacrifice 1 or 2% more energy to save carbon saving by 50%. But I don't think anyone will agree that I want to get 30% carbon savings. I should be able to get 30%, and I will have 30% energy overhead. So scaling increases carbon efficiency, but it decreases energy efficiency based on the workload elasticity profiles. So another work that we did is that we wanted to analyze the performance, carbon, and energy trade-offs. So this paper the objective of this paper to do DNN placement on heterogeneous edge resources across Europe. So in this graph, I'm showing that. So the purpose of this. Okay. So the purpose. So we were doing some analysis regarding how to optimize the carbon efficiency of model serving services. So in this graph here, I'm showing that we had a problem, and the problem in this case, we want to do optimized DNN placement across heterogeneous resources that is placed across different cities in Europe. So we had 3 policies. We had the carbon-aware policy that optimizes the carbon footprint of this deployment. We have an energy-aware policy that tries to optimize the energy that is used by all these resources, and we have a latency-aware. So we are using three metrics to analyze the benefits of these three policies. The first one is we want to see how much carbon that this service is using. Second is that we want to analyze the amount of energy that we are trying to use. And third is the amount of latency these services exhibit. Because again, we have multiple services across different edge data centers. So what is noticeable here is that every policy kind of optimizes this objective. This is no surprise. If I'm a carbon-aware policy, I should be able to optimize the carbon other than other policies. But what is interesting here is that a carbon-aware, an energy-aware policy is usually so compared to a energy-aware policy, carbon-aware policy introduces 50% carbon savings. However, it has more than 6.5 more energy compared to the energy aware. So here, if I'm considering this energy aware, it uses 6.1 megawatt hour. The carbon aware, yes, it has half the amount of carbon, but it has more than 6 times the amount of energy. So in this case, the trade-offs are not only fundamental; they need different approaches to optimize them to at least be more realistic. And the reason for these differences is basically the hardware is very highly heterogeneous in our scenarios, which is kind of reflects the state of the art right now, because most of the hardware in edge environments are very heterogeneous. There's many types of GPUs, and people have been analyzing the effect of these different types of GPUs on their total energy consumption and also carbon footprint. So the carbon energy trade-offs is very pronounced in heterogeneous settings. So in summary, I want to leave you with three things. One is that carbon footprint of computing is rising. This is something that you should now be aware of if you have not been aware of it before. Second is that if I want to consider the carbon efficiency of a service or computing or computing in particular, I should be able to analyze the entire life cycle emissions. So yes, usage is very huge for data centers, but for other devices that you are using, for example, your phone, other things are much more, maybe much more important. And lastly is that there is no free lunch in carbon hour scheduling. There is always a cost. And speaking of cost, the movements in the US regarding recycling was also claiming the same things 30 years ago. There is papers from Harvard Reviews that they analyze the benefits of whether companies should adopt more sustainable decisions in their procurement or in their things. And to be honest, there is many innovations that will happen to try to seize this trade-offs. But for now, it is there, and I don't think it's going away anytime soon. So thank you. If you have any questions, I'll be here too. So I took less than an hour, so you have 20 minutes. Using what? So usually usually at the scale of a data center, there is many approaches that proposed by data centers themselves. For instance, there is a work by Google that appears like 3 years ago or something, or maybe a little bit more, that shows that, okay, how to optimize the carbon efficiency by doing load shifting at a scale. So to do load shifting at a scale, they use something called a virtual capacity, where they can limit the usable amount of resources at different times, at different periods of time. So for instance, if I have 100 servers, maybe during noon, I can allow that the batch workloads or the entire data centers use the 100 servers. However, during night, because carbon intensity is high, I will only limit my capacity to 50%. So I'm using 50% of this workload. Also, companies use other approaches to augment their carbon intensity. To use something like PPAs, they use where you kind of invest in a local energy, in a local solar farm, for instance, and you can claim the generated green energy as yours. So both approaches are kind of used in data centers, but in the case of OpenAI, I don't know specifically that they are doing something that will help. But many companies are moving now into nuclear energy. Nuclear energy is almost as green as energy it can get. So nuclear energy are stable. They have other types of problems, but as far as the output energy that comes out of a nuclear power plant, it's green and it's stable, which is something that data centers will definitely love. Okay. So data center usually hosts two types of workloads. They host interactive workloads where latency is critical, and the results you get is also critical. So they will not really touch this. But what they do is that they want to shift batch workloads. For instance, if they have some sort of a data processing service, like the overnight data processing of YouTube videos, this can be delayed for a couple of hours and no one will really notice. Machine learning workload is another type of, I don't need to train it anytime. I can be more or less selective with the time that I train the job for, the job at. So I think we conclude. Thank you. And